So we're in this chapter dealing with first law analysis of open systems. So what's an open system? It's where you have mass flow across the boundary. And so we clearly identify an open system by clearly stating what is the control volume, the CV, the control volume. What exactly is it? Where is the mass flowing across the boundary of that control volume? And then we could apply the conservation of mass to the control volume, and more importantly, because that's typically harder, the conservation of energy to that control volume. And then we learned about the property enthalpy, how important that is and useful. It's just a convenient grouping of terms. It's U plus PV. And once we had the conservation of energy for a control volume, what was that equation? Can you write it down from memory? Can you write it down from memory? The most general form? I would encourage you to, because it'll really help you. But you have the rate of change of energy in the control volume with respect to time. That's that zone that's clearly identified, is equal to the rate at which it's flowing into the control volume by, how can heat transfer? It's going to flow into the control volume by heat transfer, minus how it flows out of the control volume in an organized energy transfer called a work transfer. Typically, I like to think of it as a shaft that's rotating. But it also could be electric wires and carrying electric power or whatever organized. It's not heat, but it's energy transfer by work across that control volume boundary. Plus, we can bring in with the mass flow, let's say there's some mass flow coming in right here, m dot, it's sweeping in with it. Every kilogram per second that's coming in brings with that kilogram certain amount of enthalpy, certain amount of kinetic energy, certain amount of potential energy. So those are the three forms that we track. We have H plus KE plus PE all on the in. That's all on the in. And if we have an out, we have minus mass flow rate on the out. We have an enthalpy, kinetic energy, potential energy, all on the exit. Oh, you have multiple inlets, do a summation over all the inlets. Multiple exits, do a summation over all the exits. That's the most general form. Do we apply it to a nozzle? We apply it to a diffuser, a turbine, a compressor, a pump, heat exchanger, and throttling device. Hopefully, by the end of the chapter, you're familiar with each one of these. And then you can describe it and analyze it. Describe that for other people. Today, I think we'll be able to cover our introduction to transient analysis. This problem, if you didn't pick it up and you took the quiz last time, I encourage you to walk down right now, pick it up. But it's a water pump problem, and it's been graded. And so you're familiar with the problem statement, but the mass flow rate of water, m dot water, is equal to 9.61 kilograms per second, part A. The exit speed of the water, V2, 2.495 meters per second. Were you able to calculate that correctly? If you weren't, do you now know how to calculate that correctly for the water pump? And then for the last part, what is the power required to drive the pump? Often, I'm going through this just to summarize the results. You have a pump. Sometimes you sketch it like this. There's a control volume around the pump. You have the inlet state 1, exit state 2, and you do have a shaft typically going into the pump. But because we're new, we want to stay with the sign convention in the first law, draw W out of the control volume. You're saying, hey, there's no pump's not producing any power. It's consuming power. I know. But when you do that, you calculate that the power is negative 85.3 kilowatts. The negative sign indicates it's into the pump. It's the opposite direction of what was sketched for the control volume. And how did we calculate that? Well, you find out that it's equal to the mass flow rate, then the change of enthalpy, H in 1 minus H2 exit. And given the states of the water, you can actually look these up in the tables. And they come in, H1 is 79.77 kilojoules per kilogram and 88.65 kilojoules per kilogram for H2.
We didn't do the kinetic energy because it didn't change?
Yeah. The diameter of the pipe is 7 centimeters and 7 centimeters. And what happens is the inlet speed is given to be 2.5 meters per second. Given you can calculate the specific volume in and the specific volume exit, you do find that it's not quite 2.5 on the exit, but it's so close to 2.5 it's negligible. Right, exactly. It would not affect probably the fourth significant digit. That's fifth significant digit in the answer. Yeah. Let's talk now about a turbine. So they have different types of turbines. A gas, steam, hydraulic, meaning what is the type of fluid moving through the turbine. A gas turbine would be like on a jet engine, aircraft, or a gas power plant where they burn natural gas to make electricity. They're going to have a turbine section, and that basically expands the gas, the combustion products. In steam turbine, well, that would be in a power plant that burns maybe coal to boil water, produce steam. That steam flows through pipes, flows to the steam turbine, passes through the steam turbine to produce power. And a hydraulic turbine is one where you have a dam. You backed up a lot of water, and it's all liquid water going through, and they call it a hydraulic turbine because the liquid water isn't changing phase, it's staying liquid. All right. But in general, you just have a box called a turbine, and you have inlet and outlet, and a lot of times we'll show W dot CV out of the turbine or W dot T, depending how you want to do their subscripts. And we do analysis for that turbine, inlet state 1, outlet state 2 of the fluid, and you write down the most general form of the first law, which we've done a couple times. Then we strike the zero terms, and then we'll have something like the W dot out of the turbine is the mass flow rate through the turbine, and the mass flow rate in at 1 equals the mass flow rate out at 2, so we don't put the subscripts on M dot, we just talk about one mass flow rate. It's operating steady state, and we'll have the enthalpy in minus enthalpy exit, and the kinetic energy in minus the kinetic energy exit. Every now and then they'll ask you to include, the elevation change. Well, then you'd have the potential energy in minus the potential energy exit. But almost always the change in elevation is negligible. It's not a tall device. These changes in kinetic energy are often negligible. And here is what really drives the turbine, a change in the enthalpy. And so that's true for a gas turbine, steam turbine, hydraulic turbine. It's really the change in the enthalpy that drives it. How do you have a high enthalpy? Think about enthalpy. It's U plus PV. Well, I'd like a large U. Make it hot. And a large PV, make a large pressure. Make a lot of it. So if you make it high pressure steam, the steam is very large pressure as well as a large specific volume. So especially for a steam turbine, this term right here can be dominant. But it's not just the flow work. It also has it's a combination of changes in U. You can expand this delta H to be H1 minus H2 is U1 minus U2. So there is a change in the internal energy, but it's also a change in the P1 V1 minus P2 V2. And often this term right there is really, really dominant. And in the reason why there's a lot of power out of a turbine. Okay? All right. Take a look. If you haven't seen steam turbines, you know, the internet is a great way to see a lot of pictures of steam turbines. You can get some YouTube videos. They can have, they're dynamic. They have multi-dimension 3D. They can walk around a real one or a simulated steam turbine. Often a big large pipe brings in steam and expands. Maybe it extends both ways through the steam turbine, is collected and passes out. You have multiple stages often, high pressure, intermediate pressure, low pressure, steam turbines, etc. Here's a quick illustration. We spend more time later in the semester on hooking the components together. We'll hook a turbine with a condenser, with a pump, with a boiler, and then the steam just flows in a loop, and the power is to drive the electric generator comes off that steam turbine, and you sell electricity. That's the way the majority of this electricity is used here on campus, is generated. Either it's nuclear here or coal-fired. That's the vast majority of electricity in San Antonio. We do have some wind, which is renewable. CPS has invested a lot of that. And we do have some natural gas. But a lot of the natural gas is used for peaking to handle the fluctuations during the day. But the power that's pumped out of the nuclear power plant, they want to run that constant. And so it's making a lot of electricity day in and day out. When they turn it on, they leave it on 7 days a week, 24 hours a day. So that steam is going in a loop through these components. But we study each of those components in this chapter. Should we solve a problem? So let's take a look at this problem. Steam at 300 meters cubed per minute. What did they just give us right here? Volumetric flow rate. At 80 bar, that's the pressure. 520, that's the temperature. Enters a well-insulated turbine. What is the key word well-insulated mean as they describe the turbine? Q.0, that's right. And they give you the inlet diameter. After you read and solve a couple problems, you realize, they're giving us the volumetric flow rate, the inlet diameter. I can calculate the inlet steam speed. If I can get the inlet steam speed V1, they probably don't want me to neglect kinetic energy, which is 1/2 of V1 squared. So you can read these problems and say, okay, I'm not going to throw that term out. I'm going to maintain and keep that term in the energy equation. 20% of the mass exits through 60 bar and 400 degrees C through a diameter of 0.3 meters. What happens to the rest? Well, the rest of the mass exits at a pressure of 0.7 bar and a quality of 90% through a diameter of 1.5 meters. That's a lot of information in those 3 sentences to digest. Let me try and make a sketch before we read what we're asked to solve for. Here's a steam turbine. We have an inlet 1. We have an outlet 2, an outlet 3, and a shaft coming out of that turbine. So we have the mass flow rate in at 1. They didn't give us that information, but we can calculate it. Maybe I should organize the information like this. State 1, and we have the mass flow rate. And it'll be in kilograms per second, because I'm going to run out of room, and I'm going to try and be very organized. And then 2, and then 3. And about the pressure. And they give it to me in units of bar. They do tell me the pressure is 80 bar. And then at the exit 2, it's 60 bar, and at exit 3, it's 0.7 bar. There's not a very large pressure drop from 1 to 2, but there's a significant pressure drop from 1 all the way to 3. And the temperature in degrees C, let's just organize the information, 520 degrees C. Then it goes out at 400 degrees C. And they really don't tell me what it goes out at for state 3, although I can probably deduce it, just like I can calculate the mass flow rates. Let's take a look at other information they give us. The diameter of the flow, and that's in meters. So the pipe diameter bringing in steam 1 is 0.7 meter. It's going out 0.3 meter and 1.5 meter. It's operating at steady state. It's rare we have a transient analysis. That's at the very end of the chapter. Determine the mass flow rate of steam that goes into the turbine. So for part A, they just want to calculate m.1. What would be the units on m.1? Kilograms per second. I'm going to pause, I'm going to walk around, I'm going to see if you can write down the equations which represent the strategy to calculate the mass flow rate in, which is m.1. Well, do they give us the volumetric flow rate?
Yes.
Use the volumetric flow rate. So what symbol, how do I represent this volumetric flow rate of 300 meters cubed per minute? What symbol do I use? X, P, T? I use the product AV, right? I think the book uses that. Or you could use Q. Some books will use Q, but this book doesn't use Q. And so what we have is that the AV, the volumetric flow rate, coming in at 1. And then if I multiplied that by the mass density coming in at 1, wouldn't that give me the mass flow rate? Volume per unit time times mass per unit volume. But a lot of times we're going to pick up the specific volume reciprocal of the mass density. And so we look over here and we say, is there a way that I can get the property specific volume in meters cubed per kilogram? I'm probably going to need it for all 3 states, so I'll put it in a table. And can you get that specific volume for the steam at state 1? 0.04313 meters cubed per kilogram. Right. And then when I'm in the table and my finger's on that line, I suspect I'm going to need enthalpy in kilojoules per kilogram. I'll just read that off right away. 3447.7. Okay. Now that I have the specific volume, I can make that mass calculation. So let me put it up here. The mass flow rate in at 1 comes in at 115.9283 kilograms per second. That's the number you store with all of those digits in your calculator. And you use for all subsequent calculations in this problem. What number do you box to represent the final answer for part A? To 3 significant digits. The mass flow rate 1 is 116 kilograms per second. Part B. What is the steam velocity at the 60 bar exit? No. Probably the best thing to do is, I didn't leave enough room here, is I need to get the velocity at all 3 states. Let me try and tuck this up a little bit. Okay, so what we can calculate is we can calculate V and meters per second. We can calculate the velocity at state 1. How would you calculate the velocity at state 1? Is the velocity at 1 equal to the volumetric flow rate at 1 divided by A1? Is that true? And so is A1 equal to pi d1 squared over 4? And so AV1 times 4 divided by pi and d1 squared should allow us to calculate V1. So anyway, we calculate V1 as warm-up, and we calculate V1 as 12.992 meters per second. Now, how do I calculate V2? Isn't that what's asked in part B? What is the steam velocity at the 60 bar exit? Well, it's a very similar equation that V2 is equal to the volumetric flow rate at 2, AV2 divided by A2. But I don't really have the volumetric flow rate. I have the mass flow rate at 2. But if I multiply the mass flow rate at 2 by the specific volume at 2, does that give me the volumetric flow rate at 2? Yeah. It's a little tricky. You got to become more and more familiar with what you have, and then that's A2. How do I get the specific volume of the steam at 2? Go to the steam tables and look it up at the pressure of 60 bar, temperature 400 degrees C. It's going to be superheated vapor, and we find that the specific volume is 0.04739. While we're there, get the enthalpy, 3177.2. See what we did? So now we go back, we say, I got the specific volume at 2, the mass flow rate at 2. What is the mass flow rate at 2? It's steady state, and 20% of the mass exits through state 2. So we take and calculate that mass flow rate 2 is equal to 0.20 times the mass flow rate inlet at 1. And I might as well, since I have the table, go ahead and put in our values as 115.9283. And then the mass flow rate at 2 comes in at 23.186. And 80% goes out at mass flow rate 3, which is 92.743. Those numbers I rounded off a little bit because I don't want to write all the digits, but I strongly encourage you, store those in your calculator. How many people have a calculator where they can temporarily store a number? How many people don't know if they have a calculator and they never stored a number in their calculator? Well, learn your calculator before the next exam. It'll save you a lot. What calculator do you have? Is it a 30 or 36? 36 is the better one, I think, isn't it? So do you have any friends that have the similar calculator? I'm going to secret the learning things quickly is to have a friend who will teach you. Or you go to YouTube and you find an internet video or something shows you how to store some numbers. Whatever. There's probably hundreds of videos on how to operate that calculator. How many people have learned how to operate the calculator by looking at a YouTube video? Only a couple? Yeah. How many people, they don't even give, when I bought a calculator, they gave us a packet. It was, quarter-inch, half-inch thick. This is how to this is the manual to operate your calculator. I used to tell students, get your manual, open it up and read it. They said, there isn't any. They tell you to go to the website and read the PDF. Anyway, let's go ahead and continue on. So the exit velocity, V2, I'm going to just say that you're able to calculate V2, and it comes in at 15.544 meters per second, but I'm going to truncate to 4 significant digits. What about the velocity of the steam at the 0.7 bar exit? That's V3. How am I going to calculate V3? Same way. So we would get the mass flow rate at 3. So V3, let me just say it's the same way. So I'm going to put the equation over here. V3 would be mass flow rate 3, specific volume 3 divided by A3. Okay, let's go to the table and get the specific volume at 3 and enthalpy at 3. But what do they tell us about state 3, which is a lot different than the other states? And I really need more room here, so what I'm going to do is I'm going to go ahead and just grab this and tuck it away somewhere else, right up in here. It's quality. That's the word I'm looking for, right? Because they tell you that state 1 we concluded is superheated steam. State 2 is superheated steam. Because they give us the quality at state 3, guess what? It's two-phase. So the quality at 3 was given to be 90%. So how do I get that specific volume at state 3? V sub F plus the quality at 3 times V sub G minus V sub F? Exactly. Very good. So we look up the specific volume of saturated liquid, look up the specific volume of saturated vapor at the pressure of 0.7 bar. Can somebody give me at least this value from the table? You have the table in front of you, right? 0.7 bar. What's V sub F?
0.001036.
Exactly, meters cubed per kilogram, right? So when we calculate the specific volume at state 3, it comes in at 2.1286. Now just compare the other value, the specific volume at 2 and the specific volume at 1. Use your hands. State 3, every kilogram is occupying a much larger volume than it did at state 1 and state 2. If you have a calculator, just do the ratio. Just say it's going out occupying 2.1286. Divide that by 0.04313. How much volume expansion did the steam experience going from inlet to the outlet? How much? About 50? 50 times? 50 times expansion. It's dropping pressure and expanding as it pushes the blades in the turbine and transfers energy to the blades of the turbine and produces work for the turbine. So 50 times expansion. Very good. So now, once we have that specific volume, the same strategy for the enthalpy, isn't it? And so the enthalpy comes in after some calculations of 2431.67. Now we'll go ahead and calculate V3. It comes out at 111.7 meters per second. And we can put that in here, 111.7. And I forgot to put in V2, 15.54 meters per second. It's coming out a lot faster, isn't it? At the exit. So that's even with a much larger pipe. A much larger, how big of a, it's 1.5 instead of a 0.7 or a 0.3 meter diameter pipe. What would happen if you put it to a 2 meter diameter pipe? Well, it'd go out slower. It would reduce the velocity. It wouldn't be so fast. Okay. Let's go. What is, for part D now, what is the total power produced by the turbine? What are they asking me to calculate, and what units will my answer be in? So it'll be this term, W dot out of the turbine, In what units? Or watts or kilowatts. Watts or kilowatts, something like that. How do we do it? We do a control volume analysis. So apply the first law to that control volume around the turbine. And what are we going to pick up for our equation? I encourage you to start with the most general form. Strike the terms that are zero and know why they're zero. But you'll get that W dot out of the turbine is equal to the mass flow rate in at 1, bringing with it its enthalpy 1, and its 1/2 V1 squared. That's the specific kinetic energy, isn't it? Then we have minus m dot 2 h plus 1/2 v squared. Both of those terms are at state 2, h2 and v2 squared. And then we have minus m dot 3 h3 plus 1/2 v3 squared. Does that make sense? And we picked up the h's while we were picking up the specific volumes. And we calculated all the velocities. And the mass flow rate in at 1, mass flow rate out at 2, the mass flow rate out at 3, those are all given. The only difficulty is what? Can you guess what the difficulty? Where would a student make a mistake? Units, 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 units. Because this term naturally is in kilojoules per kilogram. What's the speed in meters per second? You square it. How can those units be consistent if I'm going to add two terms and then multiply by the m dots? And I think I've encouraged you to do this already, true? Let me just insert a new page. Because this is one of those things where people will make a mistake. So you can either start and say 1 meter squared per second squared is equal to 1 meter squared per second squared. Leave the left-hand side alone, manipulate the right-hand side, and get the relationship you want. Or you can start with 1 kilojoule per kilogram is equal to 1 kilojoule per kilogram. Leave the left-hand side alone, manipulate the right-hand side by always multiplying by 1, unit conversions, and get the conversion factor that you want, the right conversion. So which one do you want to try? Do you want to try the left side or the right side? The left side? Okay. So if I do this, if I multiply by kilogram over a kilogram, did I mess it up yet? And then I remember that a kilogram, what is a newton? Is a newton a kilogram meter per second squared? Did I multiply by 1 again? What is a newton times a meter? Is that a joule? Is that a joule? Okay, so let's do this. Let's cancel some terms. So I know this is ridiculous that I put a kilogram over kilogram. That was a little overkill, wasn't it? So let's just do it like that. So cancel some terms here. The newtons cancel the newtons. And we're going to cancel one of the seconds. And we have meter squared goes with the meter squared. And so we have that it's 1 joule per second kilogram. Oh, it's a kilogram, a newton is kilogram meter per second squared. Both of those go. All right. But somebody said, I want a kilo over a kilo, or a kilo over 1,000. So now I have that it's 1 kilojoule per kilogram times 1 over 1,000, or it's 0.001 meter squared per second squared. So 1 meter squared per second squared is 1,000th of a kilojoule per kilogram. So that's what we wanted to establish. If I wanted to convert units, I would multiply this one by 1,000 meters squared per second squared is precisely 1 kilojoule per kilogram, that unit conversion, which would then allow me to cancel these, and I would get the kilojoules per kilogram, both terms, add them together, consistent units. And if you don't do that correctly, you're only off by 1,000, which may not seem like a lot until you start talking dollars, right? And then it's real, right? So let me just give you the answer. We're running out of room. All the pieces are here. The unit conversion has to be done. And the power out of the turbine is 99,930 kilowatts. All right. Ready to press forward? What's a compressor? Well, first of all, let me back up. Did we solve, for gas turbine, steam turbine, hydraulic turbine? No, I just picked one and solved it. And that was for the steam. I can't solve all. You have to solve a lot of problems yourself, right? And the same thing with the compressor. You have a gas compressor or an air compressor as well as refrigerant compressor. And it's just the opposite of a turbine. So I have a problem here, but in the interest of time, I'm just going to let it go. Yes, sir.
For your turbine, you said it was 3. They're all calculated like the same way?
Yeah.
Different substances?
Yeah, except for, like, say, the hydraulic turbine, it's liquid in, liquid out. So there's not a large expansion of the specific volume, but the huge change in pressure across it. So there's little nuances, but the same equations work. Yeah. All right. Let's take this approach. Yes, sir.
So what are the 2 types of compressors?
I'm sorry?
What are the 2 types of compressors?
Air, which basically is an ideal gas, or a refrigerant. Now, there can be other compressors out there in the world, but those are the 2 that you really analyze to death in this class. But let's take a qualitative look at a compressor. Here's an air compressor. Tell me, what happens to the pressure? Here's the exit state 2 and the inlet state 1. There's the compressor. The flow's going from the inlet to the exit that way. What happens to the pressure? What is the relationship between the inlet pressure P1 and the outlet pressure P2? Is P2 greater? How'd you get that? Your intuition. And knowing, okay, now that you're learning more about a compressor, that's what it is. Sometimes I have to try and describe things to students, and I don't know where to start. It's like, I don't know, I have no idea, professor, what a turbine is or a compressor is. I mean, if you have no idea, it's pretty hard, right? Maybe do a little quick Google search and just learn about it that way. Read the textbook. But the purpose is to boost the pressure. What about the diameter of the inlet-outlet pipe of a compressor? Probably not as important, but as I've shown it here, visually, which one appears to have changed? The smaller outlet. So often the outlet diameter is smaller than the inlet. Why? The pressure is so high, and you've compressed it. What about the cross-sectional area for the flow? Cross-sectional area for the flow. It would be the same relationship. The cross-sectional area for inlet's a lot larger than outlet. It's, Professor, this is an easy question. Isn't A just pi d squared over 4? Sure. Yeah, you're right. How about the temperature? Compressor. Temperature. Does it come out the same temperature? Does it come out colder? Does it come out hotter? What happens to the temperature through the compressor? Yeah, the compressor, that you're going to have a refrigerant compressor. Anybody worked with compressors for refrigeration systems? Some people have part-time jobs and all that, or summer jobs. I encourage you to do that. Get a job. related to engineering, some way, shape, or form, especially as a technician. Go out and do things. And believe me, if you've been anywhere around a refrigeration system where you're coming in, the suction line to that compressor, refrigerant compressor, is cold typically, and they insulate it. And the outlet, don't even try and touch it. It will burn you. It's so hot. How many people have ever had an air pump and you pumped up the tire in your bicycle? And you have this thing like this, and you have a little handle, and it goes up and down, and out here is a little end that goes to the bicycle tire. You know what I'm talking about? How many people have pumped up and then reached down with their finger and touched right around this vicinity? You should. Don't touch it too hard. You may burn your finger pretty bad. But you're saying, what? All I'm doing is pumping up and down. Yes, go touch right in there. It's hot. That's that kind of the outlet of the compressor. It's hot. How many have an air compressor in the shop and maybe they've seen it and they go touch it, the outlet? It's hot, right? Yeah, you can burn yourself, or you have burned yourself, huh? Maybe. So anyway, it comes out spanking hot. One other way to look at it is there's a lot of work going in to compressing it. And when you compress something, the temperature naturally likes to go up. All that work to boost its pressure makes it smaller. It's pushing. It's like a boundary work. The temperature is going to go way up. You're saying, but out of my refrigeration system, after the compressor, they put it into a condenser, which condenses it and cools it off, but it doesn't get it too cold. We'll talk more about refrigeration systems later. How about the density? What happens to the density of the fluid? Same? Does it go up? Does it go down? What's the density do? So it's more dense? Yeah, that's right. And then what about the specific volume? Just the opposite, the reciprocal of the density. So it's like that. It takes less volume for the same kilogram or pound of substance when it's compressed. All right. What about the mass flow rate? This is m dot in and the m dot exit. They're equal. They're equal. How about the volumetric flow rate? The volumetric flow rate? The areas are slightly different, true. We didn't talk about the speeds, the V's. We could do the speeds next, the speed. But well, let's do the volumetric flow rate. Which way is it? Are they the same? Well, we go back to this truthful statement that the mass flow rate in is equal to the mass flow rate exit. And we know the mass flow rate's related to the volumetric flow rate, AV inlet, times what? Density, and then the AV exit times the density. So either the AV inlet divided by the specific volume inlet, AV exit divided by the specific volume exit, or density. Whichever, my mind probably works a little better on density, because it's proportional. I just multiply it. So what happened to the density? Didn't this go up? So what happened to the volumetric flow rate? Has to go down. Is that the right relationship? And then how about the speed now? Well, this is trickier because let's leave the diameters alone. I know that the outlet diameter is typically smaller, but leave it alone. It depends on the diameter. How big a change in diameter, right? Okay. Well, hopefully that helped. I know that as you slug through problems, sometimes you're just so glad to get to the end of the problem, you don't want to revisit and think about it, but I encourage you to think about the problems and try to read the solution. What was it telling me? Does this make sense? and build your intuition. All right, now I'd like to spend a little bit of time on a pump problem. And the reason I'm going to spend a little time on this problem is because it all depends on a good selection of the control volume. So here's the problem. We have a submerged pump. It takes water from a lake and delivers it to a storage tank. So here's my depiction of the surface water in the lake, and here's my lake. It's not, I'm fighting for room. It's not a very big lake, right? And we have a submerged pump in the lake. Where are we going to put the pump? Put the pump right here. All right. So it has a little inlet pipe to the pump, and it has a large discharge that goes off like this. And it's trying to fill a storage tank, and the storage tank is way up here. And so it's transferring water up to the storage tank out of the lake. The inlet pipe and the pump are submerged 6 meters below the water level. So this distance right here is 6 meters, H1 of 6 meters. And the outlet is 85 meters above the lake level or water level. So this is the outlet. H2 is 85 meters. And it discharges into the air at the top of the tank. So it's just going to spit the water out right here, which then falls into the tank. This is a great strategy for pumping water up into the tank, because if something goes wrong, it doesn't naturally drain the whole tank and push it back into the lake. The water flow rate is given at 11 kilograms per minute. So m dot's 11 kilograms, not per minute, per second. And the pipe diameter is a constant diameter of 6 centimeters. Assume the water is incompressible. Is that a good assumption for liquid water? Sure.
Yeah.
If they didn't even give that statement, you would naturally need to make that assumption or want to make that assumption. And constant temperature throughout the system. Is the purpose of the pump to discharge hot water at the top? No. So let's say the water is always 20 or 25 degrees C through the whole system. It doesn't change temperature. Determine the power required to run the pump. How are you going to solve this problem to calculate the power required to run the pump? Yeah, but what you want to do is you want to struggle with, you're going to apply an energy balance to what? An open system which is clearly defined. So anybody looking at your work can say, I know what open system they're applying that energy balance to. And so you're going to clearly define it by introducing a control volume. And that control volume is distinguished by dashed line, which you pay a lot of attention to where you cut, where it is. So can you please introduce, and I'm going to pause, walk around, a nice control volume that you would like to apply to this problem. And there are multiple candidates, not just one candidate. So which is the control volume that you want to use? All right, I'll pick it up here. So what do we have is we could sit there and say, and the number of people said, well, I'm going to draw a tight control volume around that pump. The inlet to the pump, I'm going to cut. I'm going to come around the pump, and the outlet to the pump. That's my control volume. A number of people did that. And then it's really just like what we did. We just focused only on the pump without any piping system. True? But do you know the inlet pressure to the pump? No, and basically that's the question for part B. Do you know the outlet pressure from the pump? No, and that's the question that you need to answer for part C. So it's not the most judicious control volume. You want to select a control volume such that it's going to have the boundary where water comes into the control volume at a known pressure and goes out at known pressure and elevation. So a lot of people say, it really doesn't, I'm going to try and change color to green here, really where you cut it in the air, because there's no water cutting across the boundary of control volume in the air. So it really doesn't matter if I have a box or just follow closely the pipe. But when I come up here, I need to cut right there. I need to cut at the outlet to the pipe. That one's pretty easy to get. Pick that one. Cut to the outlet of the pipe, come over here for the air. But how does the water get into a nicely defined control volume where I know the elevation and the pressure? So it's really finishing off the control volume down by the lake, right? So any suggestions what it should look like? Let's say somebody just said, hey, you want a control volume? There's your control volume. How does the water go into the control volume?
It's on constant going down.
For this control volume, there's no water crossing the boundary of the control volume. Does that make sense? So this is not a good control volume. I need a control volume where water actually is... Now I erased everything. Sorry about that. Here's my boundary of the lake, like that. Okay.
The exit valve of the pump?
If I draw it at the inlet to the pump or the exit to the pump, I don't know that condition. I don't know the pressures there. I'm going to be asked to solve for part B and part C in a second. Come on, use your imagination.
Is the pipe going into the water, or is it...
The pipe is underwater at the same location. It's just a small little draw into the pump. So I'm not putting the pump is submerged and the inlet pipe is submerged at the same depth in the lake. Yes?
Right before, like right as like outside the lake.
Well,
So just physically defined.
let me try this. Edit. Here, try this. Edit, copy, insert, new page, edit, paste, and blow this up. Maybe that's it. Maybe I need to really focus in on where am I talking about, right? And so, some people really want to either do the outlet of the pump, cut right there, and then continue the control volume. But I don't know the pressure there. I know the elevation, but I definitely don't know the pressure there. How about cut right here? But I don't know the pressure there either. Is the pressure at the inlet to the pump, is that pressure equal to rho g H1, where H1 is 6 meters? No, it's not. We're going to find that it's close to that, but in order for water to flow into the pipe at the inlet of the pipe, do you think it's going to be greater or less than that? It's going to be less. It's going to have a little suction to get it into the pipe. But why don't you take the control volume and take it all the way like this and around like that? You say, what? Put the control volume an inch below the water level. As I start to turn on that pump, what do you think about the water level in the lake? It's basically going to be falling into this right here. It's going to be dropping the level of the water level of the lake, true? Do I know the pressure up here an inch below or a half an inch below? Yes, with confidence. It's atmospheric pressure. True? And if it's a large lake, tell me about the velocity of the water that's sort of falling, the water level's falling. Are you going to be able to see it? Unless it's a really small lake and a huge pump, you're not going to just see it drop. You're going to just see a very slow. So what's the speed of this velocity of the flow coming in at the across this boundary of the control volume, V1? Approximately 0. Right? Also, right in here, didn't you have some fast-moving flow at the inlet to the pipe to the pump? Yeah. It's got the same speed because it's got the same speed at the suction as the discharge as anywhere in the line, and as well as the exit to the pipe, because the pipe all has the same diameter. Okay. So now that we have this control volume, which is enlarged, what would be, it cuts through the concrete or the soil, and it goes along the bottom surface because there's no water coming through that part of the boundary of the control volume. This is the section right here where the water comes into the control volume. This is the section where the water exits. That's the logical place to call 1, and that's the logical place to call 2. True? Okay. Let's go back to our problem then. With that enlarged control volume, let's now calculate the power required to run the pump. So I'm going to draw it because of the sign convention. This is W dot CV out of the control volume. It's a shaft power to drive the pump. And we write the first law for that control volume, and we'll get the W dot CV is equal to the mass flow rate of the water. We have the inlet enthalpy minus the exit enthalpy, and then we have the inlet 1/2 V1 squared minus the 1/2 V2 squared, changes in the kinetic energy, and then we have the G Z1 minus Z2, the change in the elevation. So I didn't neglect the changes in the kinetic or potential energy. I kept them in the energy balance equation. All right, let's talk a little bit about this H1 minus H2. Is that U1 minus U2 plus P1 V1 minus P2 V2? Where exactly is state 1? The water level at a lake. Where is exactly state 2? Discharge at the end of the pipe high above the tank. So, did the temperature of the water change? Did the internal energy of the water change? No. Did the specific volume of the water change? Is it more dense? No, it's incompressible. How about the pressure? Atmospheric pressure, both of them have the known pressure with confidence. So guess what? The change in the enthalpy is 0. Now I say, what is the speed 1? What's 1/2 V1 squared? V1, that's the inlet velocity at 1. 1/2 V1 squared is negligible, 0. Why? It's a large lake. We just talked about it. So what about the discharge velocity? Should I discount that, make it 0? No, it's spitting it out the end of the pipe with some speed. Let's keep it in the equation. How about the elevation change? That's what the pump has to do, has to lift the water. So what we can read this equation. The power to drive the pump is proportional to the mass flow rate. You have a larger mass flow rate, you can need a bigger pump, more power to drive it. And you can read it as you have G Z1 minus Z2 minus the 1/2 V2 squared. So if I had to say it, I would say this is the energy per unit mass to lift it, and this is the energy per unit mass to spit it out the pipe. So let's go ahead and put our numbers in. It's 11 kilograms per second, 9.81 meters per second squared, and then we have an elevation change. Where is Z1 minus Z2? This is state 2 at the exit. There's 1. What is Z1 minus Z2? Is it negative 85? Then we have minus 1/2. I need to calculate V2. Did I calculate it already? But I think you know how to calculate V2 pretty easily, right? V2 is the mass flow rate multiplied by the specific volume divided by the area of the pipe. And the V2 comes in at 3.8 something. 3.89045 meters per second, then you square that. And now this is W dot CV, and we calculate that it's going to be negative 9.256 kilowatts. Again, watch your units. We're going to use that 1,000 meters squared per second squared is 1 kilojoule per kilogram. That unit conversion right there. Why the negative? Because it's not out of the control volume. Its pumps consume power. So it's into the control volume. But this is a good answer given that we show the direction out. A lot of work for part A, isn't it? Now, what is the pressure at the inlet to the pump? What's the pressure to the inlet of the pump? For this part, select a new control volume. And I want to see if you can select a different control volume which will help you with like laser guided precision get the answer for part B, which is the pressure at the inlet to the pump. I'm going to stop, walk around, see if you All right, so for part B, it really is all in the selection of the control volume. And so let me jump back to this slide. Maybe I need to clean it up some. Well, here, let me do an insert a new page. I'll redraw our lake, redraw the inlet to the pump, redraw the pump, redraw the pipe that goes and discharges, redraw the level of the water in the lake. The discharge is definitely above the water level in the tank. We don't know how high it is above, but that's the discharge. So this distance from here to here is 85 meters. And this distance, the intake is submerged and the pump is submerged 6 meters below. Okay. So last time we had a control volume which cut right here and then went around like that and then came up like that and went like that. That was our control volume, wasn't it? I would take a subset of that control volume to analyze and get the pressure at the intake of the tank, or of the pump. That's what we want, the pressure. So maybe I introduced, and we call this state 1, and then this is state 2. We'll leave those states alone, and we'll talk about state 3 and state 4. The inlet to the pump and the discharge from the pump. And I want to know the pressure at state 3. Well, some of us have picked a control volume that goes like this. That is just like here, it comes down, but then it just cuts right there and goes up. That control volume will work. And when you draw that control volume, it's critical whether or not the pump's in it or not in it. Because if you leave the pump out, it's like a free body diagram with some forces or loads. It's not going to get the right answer, right? So that control volume will work. But there's another control volume, which is the other half or the other part of the previous control volume. What is that control volume? It goes like this, like that. I think you should be able to analyze it with both of those control volumes. Here, it would just be, for that one, it would just be from one, let me try and draw it this way. From 1 as an inlet, 1 as an inlet to 3 as an outlet to the control volume. Is there a pump in that control volume? No, the pump's not in that control volume. So let's do this. Let's draw the first law analysis for this control volume with no pump. You have W dot, well, let me do the, it's trying to conserve room here. Well, you're going to have the rate of change of energy, control volume with respect to time. It's steady state. The rate at which flows in. heat flows in? Nothing. Do we have any power going across? No. And so all we're going to have is the mass flow rate in at 1 times the enthalpy in at 1, which was U plus PV. We already saw that that was H. Well, the mass flow rate in at 1 is the same as the mass flow rate out at 3, so that's the same m dot. H1 minus H3, but we already saw that those are the same. Are they? No, not for this case. You have to be more careful. We have 1/2 V1 squared plus 1/2 V3 squared plus G Z1 minus Z3. Did I do that equation right? So the mass flow rates really is irrelevant, and what we're left with is,
The velocity subtract on them?
now this velocity 1 is still negligible, but not the velocity at 3, is it? Because that's right at the inlet to the pipe. And so it has to have that speed in the pipe coming in. So we know that the speed 3. Let's talk through this H1 and H3. It's U1 minus U3 plus P1 V1 minus P3 V3 plus 1/2 V3 squared plus G Z1 minus Z3. Did I do that right? You follow? Let's get rid of these two. Why? The temperature is not changing. There's no, and liquid, incompressible, the internal energy is essentially a function of temperature. Okay. How about the specific volume, V1 and V2, or V3? Are they the same? Don't cancel them, but just note that V1 and V3 are the same. Okay. What about P1? Well, how about this? I'm trying to find P3, the pressure at the inlet. That's where it is in my equation. I need to find P3. So you can rewrite this as P3 is equal to P1 plus G Z1 minus Z3 divided by the specific volume, which is constant, plus, I'm trying to do this all in one step. Put the P3 over on this side, then you have the P1, you divide through, so that's a plus. So it's 1/2 V3 squared, there. That's a minus sign right there, isn't it? That's a minus sign right there. 1/2 V1 there, V1 squared there. So this is a minus. Okay. You see how we got that equation? So somebody said, isn't the pressure at the inlet P3, isn't that just rho G H1? This H1 is 6 meters. Well, what's this part? Rho GH1. But you subtract off this part, and that's the difference. So it's close to the hydrostatic, but it's slightly different. So what would be this atmospheric pressure is 101.3 kilopascal. The hydrostatic, due to the elevation of 6 meters, 1,000 kilograms per meter cube for the density of the water, that gives like 58.86 kilopascal. And you subtract off 7.57 kilopascal. What's that from? It's accelerated, and it's now moving into its, you have to have suction to get it to draw into the pipe, and that's the suction due to the speed. From the energy equation, you see that. So somebody may say, this was roughly 60, and this is roughly, what, 8? 60 minus 8. So if you neglected that there was suction at the inlet to the pipe, you missed it by the difference between 60 kilopascal and 52 kilopascal. You might say, well, that's not much. Well, but it's something. True? So this is important but not overwhelming. It's not dominant. It's just significant. It's important. So the final pressure, if I wanted to calculate it, atmospheric pressure, the total pressure accounting for atmospheric pressure would be 152.6 kilopascal. Next question, for part C, what was the outlet pressure from the pump? That's pressure at state 4. How would we calculate the pressure at state 4? You could do a control volume only of the pump. You could do a control volume of the inlet at the lake level and include the pump. Or you could do a control volume only from the discharge of the pump to the discharge of the pipe. There's 3 control volumes. Since we've worked this problem so much, all 3 of them are, I think, equally easy. Does that make sense? You could do, let me try and draw it. You could draw a control volume like this, but include the pump, and now the discharge is at 4. You could do a control volume only around the pump because you already know the inlet pressure, P3, to the pump. Or you could draw a control volume that is 2 down to 4. All 3 of those will work. Well, let me leave you with the solution. I think that if you were able to follow so far, you're able to calculate the pressure at 4. Intuitively, how big a pressure at 4 do you think you get? High. It'll be almost rho GH, where the H is this 85 plus 6. Yeah, almost. But the pressure at 4 comes in at 994.9 kilopascal. So the pressure increase across the pump, the last part of the problem, that would be delta P of the pump is equal to P4 minus P3. And you just make that calculation. It's like 1,000 kilopascal minus 150. Yes?
Where did you get specific volume for solid P3?
Yeah, you'll just know that it's liquid water. And we're going to use the density is 1,000, or specific volume is 0.001 meters cubed per kilogram, or kilograms per meter cube. You assume it for water. It's slightly temperature dependent, but it's no mention of temperature, so I just grab it. Yes?
And on the P3, you just divided out the volume, the specific volume 1 over volume 3 ratio, because it was the same.
To go the algebra from this equation to that equation? Yeah. I'm dividing through by specific volume. Yeah. Any other comments or questions? What did this problem teach us? Carefully identify your control volumes. Take some time there. Try to, where you know the inlet flow as well as exit flow. And so let's move on. Heat exchanger. Well, what's a heat exchanger? A lot of times, the heat exchanger has 2 fluids. One is a hot fluid flowing maybe one direction. Here I show it from left to right. And a colder fluid flowing in the opposite direction, flowing from right to left. This is very common. So what do we have? We have an interface between the 2 fluid streams, and you have a heat transfer across that surface within the device called the heat exchanger. This always threw me for a loop. I would be, what? What did they just say? A lot of times they'd say it's an adiabatic heat exchanger. What do you mean by adiabatic? What does the word adiabatic mean? Does that mean constant temperature? No, constant temperature is isothermal. Adiabatic means no heat transfer. No heat transfer. Wow, this seems like a silly heat exchanger. If you have an adiabatic heat exchanger, that means no heat transfer heat exchanger? No heat transfer with the surroundings is what they mean. So when you see the word adiabatic heat exchanger, just clarifying the heat exchanger, there's no heat transfer from the device to or from the surroundings. No heat transfer, let's say this way, Q dot from to the surroundings is equal to 0. That's what they mean. It doesn't mean that there's no heat transfer within the device. Often that's the purpose of the device, and there's a lot of it. Okay. Well, so how do we analyze these? Well, you just have to start numbering your states. Maybe state 1 is the hot in. State 2 is the hot out. State 3 is the cold in. State 4 is the cold out. And you then know that there's no shaft power cutting across a control volume and closing that heat exchanger. There's no heat transfer. It's an adiabatic heat exchanger. Often the changes in the kinetic energy and the changes in potential energy of the flowing fluids are 0. You just get a very simple equation that the mass flow rate of the hot fluid times the enthalpy change of the hot fluid is equal to the mass flow rate of the cold fluid times the enthalpy change of the cold fluid. And that's the energy balance for the heat exchanger. I wouldn't memorize it. I would just be quick to derive it and then be able to read it, understand it. Here's a bunch of questions. What is H1 compared to H2? Greater, equal, less for the hot fluid. H1 is greater. That's exactly right. How about H4 compared to H3 of the cold fluid? Greater, equal, less? H4? Yeah, it's going to be greater, right? Because it's picking up heat. It's going out warmer. Okay. What you can do is sometimes I'll do an analysis of 1/2 of the heat exchanger. And basically the Q out of the hot is equal to the mass flow rate of the hot times H1 minus H2. And that, if I look at the other half of the heat exchanger, is what's flowing into the cold. And that's equal to mass flow rate of the cold times H4 minus H3. So what flows out of the hot flows into the cold. Energy is conserved. There's no flow to the surroundings. Don't have a problem. I don't have time to solve this problem, so I'm going to go ahead and skip it. And I want to get to throttling devices. Are you still with me? Are you still awake? Because this is one of those, like, what are we talking about? So I encourage you to take a look at what they online dictionaries. What's a throttling device? Well, it's a generic term used for any device that simply dissipates pressure energy by inversely converting it to thermal energy. It's like a nozzle or diffuser, or unlike nozzles and diffusers, the throttling devices provide no form of useful energy recovery. Basically, you have a capillary tube, a porous plug, some adjustable valve. Those are all examples of throttling devices. Where do we see throttling devices? Your home refrigeration system, your refrigerator. You ever look in the back of it? Look underneath of it? Encourage you to do that, but don't get electrocuted, right? Be careful, if it's running. But has anybody ever done that? You should pull out. You probably have a little owner's manual with your refrigerator, and you're probably supposed to vacuum or clean the coils every once in a while, like every 5 years or so. And you probably look under there, and there's a gob of dust and matted up, but it's supposed to be a clean heat exchanger surface. Anyway, a lot of times in the refrigerator, home refrigerators, you can find the capillary tube very easily. It's just a coiled up thin copper tube, and if you can trace the refrigerant, it flows out of the condenser through the capillary tube, and in the capillary tube there's a pressure drop, and the liquid, it basically is ready to evaporate in the evaporator. Most of it's liquid when it comes out of the capillary tube, some of it's vapor. But this is not a joke. They're all over. And you can find them typically, I would say more than half of you have one in your kitchen or in your any refrigerator. If you have a dorm and you have a little refrigerator type on the desktop, you could probably see it. Just turn it around, look at it, look underneath. Okay. Porous plug is less common, but we have adjustable valves. A lot of times the air conditioning system has what they call a thermostatic expansion valve, TXV, and it's actually controlled. There's a feedback mechanism to it where they're moving something that pushes down, it seals, it cuts off the flow, or it moves up, it lets more mass flow through the system. But there's a big pressure drop across that device. It's a valve, and it could be controlled automatically. Here is an A coil. Anybody ever heard the term A coil? Most of you in your houses or apartments have evaporators in your air conditioning systems. It's an A coil. It's shaped like an A or upside down V. I don't know why they don't call it a V coil. They all call it an A coil. Doesn't it look like more like an upside down V? Where's the part that goes to make it an A? I don't know. It's missing, but don't worry. It's an A coil. And airflow comes up and goes this way across the coil. It's warm and it comes out cool, and then it gets distributed to your house. And right here is a thermal expansion valve. That's a metering device. Okay, it's a throttling device. So they're all over. In the automobile, I have one upstairs. I was going to bring it, I forgot, and I could pass it around. Some students said, I work in shop, here's one. You can use it as a demo. Anybody work in shops, know what the air conditioning metering device is? Yeah. They have different ones. There's some of them are really simple. The inline has a, I got one upstairs, I forgot what its name is. A student gave it to me. As well as another one which is like aluminum block. And it actually looks like a TXV. It has a little circular diaphragm on top that help accentuate so that you can lift a needle off of a small passageway to control the flow through it. Anyway, what we need to do is we just have to analyze a throttling device, and the purpose is simply to have a high pressure drop across it. No heat transfer, no work transfer. They use often in refrigeration systems. I don't know if I have enough time to solve this problem, but let me set it up. So we have ammonia at a given flow rate of 0.2 kilograms per second. It's coming on at a high pressure of 12 bar and a temperature of 20 degrees C. It flows into a throttling device, so it goes like this into a throttling device, and often we sketch it like that. That's the illustration of a throttling device. And it exits that throttling device at a pressure of 1.5 bar. What happened to the pressure? A significant pressure drop. And then the ammonia then flows into a heat exchanger and then exits the heat exchanger as saturated vapor at a pressure of 1.5 bar. What happened to the pressure change through the heat exchanger? Negligible. It's just constant pressure. So we talk about state 1, inlet, state 2, after the throttling device, and state 3, after the heat exchanger. Neglect changes the kinetic potential energy. Determine the temperature of the ammonia after the throttling device in degrees C. So it comes in at 20 degrees C, goes through a throttling device. What about the temperature at state 2? What do you think? Going to be greater, equal, less? Is there any heat transfer into this device? No. Most time, students see this. You know what they're going to say for their best guess at the temperature at 2? They're going to say, I think it's the temperature at 1, it's 20 degrees C. And this is the miracle of refrigeration. It's incredible. You describe the fluid coming into state 1. It's basically subcooled liquid. It's a liquid state. It could be saturated liquid, but if you look up ammonia, my guess is it's liquid, subcooled liquid. Let's take a look. What is the saturation temperature, Tsat, for ammonia at 12 bar? The first one to get there, tell me what table you're in. 30.94 degrees C. So that's the saturation temperature. The actual temperature is 20 degrees C. It's colder than the saturation temperature. So state 1 is subcooled liquid. It's in the liquid state. It passes through this throttling device, the pressure drops. We do an analysis, first law analysis of this throttling device. What do we conclude for the throttling device after we do a first law analysis? Is that the exit enthalpy is equal to the inlet enthalpy. It's isenthalpic. It's not isothermal. It's not isobaric. It's not isochoric. It's isenthalpic. So what we do is we come back here and we say, what is H1 approximately? Do they give us a subcooled liquid table for ammonia? No. So we have to use the approximation that it's H of F at 20 degrees C. It's the saturated liquid enthalpy at 20 degrees C for ammonia. We pick that value off. We get that it's 274.26 kilojoules per kilogram. Now, how does that help us determine the temperature at 2? Well, H2 we now know, 274.26 kilojoules per kilogram, first law. These two properties are both intensive, independent. Hence, in theory, I can get any other property. I'm interested in the property temperature at state 2. So how am I going to get the temperature at state 2 knowing pressure and enthalpy? Well, we have to find out what state is is it superheated vapor, two-phase liquid vapor mixture, or is it maybe subcooled liquid still? We go to the pressure table at 1.5 bar, and we look at H of F at 1.5 bar and H of G at 1.5 bar, and we pick those out of the table. H of F at 1.5 bar is 65.32. H of F is 1410.61. And we compare. Is 274 less than H of F? If it was, it's subcooled liquid. Is it greater than H of G? If it is, it's superheated vapor. If it's in between, what is it? If it's in between the H of F and H of G, it's two-phase liquid vapor. There's a given quality for it. Can I calculate the quality at state 2? Well, that's the actual H at 2 minus H of F at the pressure of 2 divided by H of G minus H of F. I calculate the quality at 2. We find that the quality at 2 is 0.155. What does that number mean? It's 15.5%. What does that mean? That 15% of it's in the vapor state, in the gas state. What about the 85%? It's in the liquid state. They're both at the same pressure, and they're both at the same temperature. Can we now look up what is T2? What is T2? Is it the saturation temperature at 1.5 bar? Sure. And so T2, let me draw it here, comes in at a whopping, this is incredible. Most people don't believe me. And a lot of people will forget this after they leave this course. But it comes in at what temperature? Negative 25.2 degrees C. this device is almost magic. It takes fluid in at 20 degrees C. It produces fluid at negative 25 degrees C. There's no heat transfer in this device. There's no work transfer in this device. How did that work? You really, really, really need to think about that. I encourage you to think about it. What was the big change? Pressure. When it dropped pressure, what did the fluid want to do? Vaporize. Some of it did vaporize, but it takes energy to vaporize fluid. And so it came at the expense of the liquid's energy, and the whole mixture dropped in temperature because some of it vaporized. And that's it is really incredible that you have vapor compression refrigeration systems that work. So what's the temperature after this heat exchanger when it comes out saturated vapor at state 3? What is the temperature at 3? Well, did it change pressure? It just, all of it boiled, but when every bit of it vaporized or boiled, it really boiled at constant temperature, didn't it? When it was boiling, it was absorbing heat, but the temperature stayed negative 25 point. Guess what the temperature is? Negative 25.2 degrees C, the saturation temperature. Answer for part B. And what is the heat transfer to the ammonia in the heat exchanger? And look at the units they have, kilojoules per kilogram. They're asking you to calculate Q dot per M dot of the refrigerant, which is, let me draw it down here. Whoops, get rid of that. Lowercase q is a symbol often used for that. It's Q dot divided by M dot. It's going to be the H at 3 minus the H at 2 from an energy balance around the heat exchanger. And when you do the calculation, you calculate that it's 1140 kilojoules per kilogram. You absorb a lot of heat per kilogram of refrigerant flowing through the system. Okay, sorry we're a little rushed there. We'll see you Thursday. Hey, Professor, what happens 1 week from today? 1 week from today? Exam. If you didn't pick up the quiz last time, it's on the table. Thank you for your attention.